All right, welcome back. We are Game 2005. That's game physics in the fall 2021 semester at George Brown. And it's week one, part one of our broadcast. And today we're going to be doing a course intro orientation. And we're also going to be talking about geometry and trigonometry a little bit, which is where we start physics off with. Okay, let's talk about our who I am and what's the schedule. Most of you know who I am, but if you don't, if you're new to the course or you're transferring in from another program or you're coming back from a hiatus, my name is Tom. I'll be your instructor for this semester for the lectures only. There will be a lab instructor that's different from myself. It'll be Joss. He'll be joining you during your lab sessions that are scheduled throughout the week. We meet, that means for lectures, every Thursday between 11 and 1. Let's take a look at my schedule because I printed it recently, and it looks like that's the time frame. 11 to 1, yes. All right, so when we get together, right, every single time, I'll be talking about the theoretical part of the physics lectures, and then I will go over the assignment requirements and all those kind of things, and then in lab, you and the lab instructor will go through techniques, on how C++ programming techniques. You're going to be using the SDL engine that I shared with you guys last semester. And one day, Neil will actually incorporate your documentation. Neil has been very kind and documented quite a few parts of it. So we'll get into that as well. Hopefully get that release done very soon. Will we have quizzes on theory? You will. And I'll talk about that in a bit. All right, so let's talk about our schedule a little bit as we go forward. Again, this class is being recorded. It's up on YouTube. If you're interested in watching the YouTube feed, because you're better off with closed captioning and you're not a native speaker, an English native speaker, and you want support, you can certainly look at the YouTube feed. You can get it right here up on Blackboard. All right, so this week we're going to be talking about geometry and trig review. It's a bit of an orientation. You'll have a chance to learn about the SDL framework again, or remember what it was if you forgot. If you're coming back from a semester off because you were off during the summertime, you'll have a chance to look at the code base again. It's improved a little bit, and it's going to continue to improve every time you see it. But for the most part, that's the framework we're going to be using this semester. Again, if you notice, our meeting times and dates for our lecture only are listed here, September 9, 16, and so on. We're going to start with geometry and trigonometry. We're going to start talking about motion in one direction next week, and assignment 1 will be assigned, and it'll be due in 2 weeks after that, okay? Assignments, for the most part, are there's some individual stuff, and there's also some assignments that are group assignments. And I'll talk about those as we go forward, okay? So the laws of motion we hit on September 30th, so that's the 4th week. Circular motion, we talk about energy of a system on the 6th week, and then that's when assignment 2 is due, just before the midterm tests, where we will have no lectures that week. You'll have a chance to do your midterm test. It's a true-false multiple choice test. Chef Cat asked that question. And it'll be due at the end of the week. You get it at the beginning of the week, and it's due at the end of the week. You have the entire week to do it. You'll get multiple attempts to get it done. Okay? I'm not sure why it's down on Microsoft Edge, but it looks like it's working for me. And let's just make sure that it is and it's not down. So if I go to here, and if I go back to here, then it should be working. If this was down, it wouldn't work for me either. So I think we're okay. Okay. All right. In the second half, we're going to be talking about projectile motion. We'll be talking about collision detection and response in more detail than we have in the past. It's all open book. Yeah, absolutely. And then when we get to the 3D part, 3D collisions and 3D response, I will allow you to use the Unity game engine, right? Only for the graphics portion of it. You won't be allowed to use rigid bodies that are built into Unity or the Unity physics system. You'll have to make your own. Okay, so that is the good part about it. But you'll be focusing on 3D collisions and 3D collision response in the second half as of week 12. Joss will be going over with you the Unity game engine earlier on to get you geared up for being successful with assignment 4, all right, where we do more of the 3D stuff. As well, your final test will be practical, and it will ask you to do something that typically I think it is practical, if I'm not wrong, and it'll ask you to do something that is related to 3D collision detection and response. We're also going to have a special topic that's going to hit us on week 14, which is particle systems that we're going to be discussing in more detail and how those work. Okay, so that's really the schedule for what we're learning. It's very specific on motion, the basic laws of physics. We're really focusing on Newtonian motion. When it comes to physics and game physics in general, we really don't talk about things like thermodynamics or other kinds of physics. We focus on motion, kinematics, those kind of things. Yes, I'm pretty sure, Shimron. Pretty sure. I'm going to check to make sure, but I think the fourth one is. It might be the third one as well. But I'm pretty sure the first 3 are in 2D and the last one is in 3D. So a bit of a departure. The last one's a little bit more difficult to do. And the reason for that is because you have to kind of really create your own structure in the Unity game engine. Some people think, wow, okay, I'm using the Unity game engine, I can do everything. But then when they start doing it, they realize how difficult it is. All right. Evaluations. You're going to be basically getting 12 labs approximately, and you're going to get the best 10 out of 12 labs. That's what you're going to get. Assignment 1 is simple motion. Assignment 2 is 2D motion. Assignment 3, there you go, 2D collisions, and assignment 4 is 3D collisions. And you can see the weighting goes up as we go towards the end of semester. Your midterm, which is theoretical, is worth 20%, and that's in week 7. Again, no classes, no lectures during that week. You will have labs, but your labs are there, and your lectures and lab times are there to accommodate you if you need assistance with any of the questions. I will still be here during that time. We will get together on the Thursday between 11 and 1. It'll be an opportunity for you guys to get together and complete your at least one attempt of your midterm test. Final test is the same. There will be no lecture during that week, the final week of class, but rather we're going to get together and I will give you support on your during that day on any questions you might have related to your final exam. All right? All of the tests and the exams, anything like that we do, they're all due at the end of the week. So you get them at the beginning of the week. They're due at the end of the week. You have multiple attempts. Miguel asks, is it on the last semester engine or a new one? The same one from last semester. All right, so that's the one that I gave you. So it's not, yeah, I think I'll make it Sunday, Neil, so that way it gives you a good chance to, to have the whole week to get it done. Okay. Let's continue. Assignment videos. I know you guys love assignment videos, but I'm going to talk about assignment videos again. Assignment videos are required. Okay, so they're not something that are optional. When you create your assignments, as an example, you need to submit a working assignment video. On that, there are some people who are right now learning from other countries, and I have to respect that. So on that, I will allow other streaming providers other than YouTube, as long as I can access them, and or if you want to share your recording on Google Drive. What I will not allow is a assignment video that is done in a video format uploaded to Blackboard. First of all, Blackboard won't even allow it. There's limitations on how much you can upload. And I don't want to download your video. Please don't zip up your video or anything like that, or zip up the link to your video or your GitHub link. Make it available in your submission text so I can access it right from there, right? And same thing with our lab instructor. When you produce labs, right, usually what the lab instructor will do, and this is on Joss, how he wants to run them, but typically what we do is we ask you to follow along. It's a follow along exercise. he will give you something to build capability with C++ and physics, and that supports the assignment requirements. That's what he's going to do, okay? And your labs are for marks, and they're usually due typically at the end of the week, all right? So again, follow up with Joss. He'll give you more details next week when he starts doing all the lab instruction. That's when it's going to start next week. Okay, so lab assignments, as an example, sometimes they'll ask you, Joss will ask you for a video. There may be some, exemptions to this. He might ask you to do screenshots like I've asked you to do in the past. It's really up to the lab instructor what he wants you to do. But for assignments, any kind of assignments that you submit, you must submit a video, okay, for you and your partner together. So example, it says you have one PowerPoint slide. People forget to do this for whatever reason. There's only one slide. You make one slide as an intro slide. I'm spending time telling you this because that's how important it is. Shaftcat, you're going to have to watch the video on that one. I got to move on. But basically what it is for your slide, you make one slide deck, right, as an example. And the slide deck itself, and is there a lab this week? No. You make a slide deck, but the single slide in there, it has to have your name, your image of you, and your partner. So no avatars, can't put any kind of anime or something weird to represent you, or a logo or something, or it's got to be an image of you, a current image. And that includes your full name, your student ID, the course code, the course name, and your assignment information. What assignment? And when you start your video, you're gonna start with that slide, okay? You're gonna say, hi, my name is Tom, as an example. And my student ID is whatever the student ID is. And I'm making a video for GAME2005, physics, game physics, at George Brown, and it's for assignment 1. Example, right? And then each group member here, I want you guys to have some presentation time for each group member. If you're doing group assignments, both members should say something, do something, okay? Even though one member can present the main thing, our partner's mandatory. I'm not sure that I made them mandatory, right? As an example, I don't think I did. And I'll talk about that in a bit. But however, I recommend it. I recommend it. It's going to alleviate some of the pressure. And again, certain assignments may not allow it. I'm not sure if the first one does. I know that assignment 2, 3, and 4 do allow it, but assignment groups should be no larger than, I believe, 2 or 3. And I'll talk about that in a bit. You need to give someone something to do is the thing that you need to do. There's lots of stuff in the assignments, and I'll talk about the assignments. I'll give you a sample. You'll have the assignment next week, but there's got to be a reason. Everyone's got to do something, okay? Each group member will be required to present. You will demonstrate your application's functionality, so the thing you're going to make for me with the STL framework, and you will explain your application's code. How does this thing work? 2005, game 2005. All right. The most important thing is if I can't hear your video and I can't see your video, one or the other, obviously it's useless to me. So if I get a video that I can't hear and I can't see, it's not a video. It's not useful. You'll get 0. And I won't mark you on your submission, right? Until you submit something else. Videos shouldn't run long. Okay, I don't expect you guys to produce a Academy Award-winning video with cuts and everything else. I don't expect you guys to be editors in any way. 5 minutes, non-edited. I recommend OBS to produce it, and it's something that you're going to submit a link to, something that's clickable. Again, you can use OneDrive. If you want to use OneDrive instead of YouTube, you want to kind of host it there, and then I can click it and run it. Or it could be on Google Drive, whatever, but it has to be something that's clickable, not something that I'm going to download from Blackboard. Please don't make a 30-minute short film. Okay, I won't look at it, Kai. Just letting you know. All right. Any questions around the requirements and the course structure? Again, course structure, 2 instructors, myself for the lecture, Joss for the labs, and he's going to introduce himself next week. Okay. Let's continue. So let's start, I think is the best way to say it. So really what we want to start talking about today is geometry and trigonometry. One of the challenges that students have when they first start off is they've forgotten geometry and trig. If you don't know geometry and trigonometry, physics becomes very challenging, okay? So that is the way we start. So in this section, what we're talking about is an overview. What is geometry and trigonometry? Why is it important? What are angles? You know, I know that you might think this is crazy that I'm talking about such basic things, but people have forgotten. People have forgotten about triangles. Without triangles, really, you can't do any physics calculations. Without triangles, you can't really build stuff, you know, for games. Triangles are kind of like, I would say, the building blocks for how to make everything, right? So, triangles, and more triangles. Triangles require trigonometry a lot of times to figure out. And we start with triangles and geometry. So let's think about this for a second. So what is geometry, right? It's the study of shapes and space, and particularly symmetry. A lot of the stuff that we do, when you notice in physics, is symmetrical, right? So if we have something on one side, typically we have something on the other side. If there's something that we have to balance, a lot of times we have to create a balance between forces. There's symmetry involved, and we're going to be talking about those things, right? So again, in this section, we're really talking about angles and triangles. And the area of mathematics that covers triangles typically is trigonometry. Trigonometry deals with things like sine, cosine, and tangent in order for us to solve the triangle, right? There are some formulas, right? And some proofs that we can use to solve the triangle in order for us to understand all the angles that are required. Now, you might think, wait a minute. Why do I care about those things? I'm talking about physics. Yep, you're right. You're talking about physics. But you need to understand trigonometry and a bit of geometry to understand how shapes intersect, right? So example, when we do collision detection and response, how do they intersect? How do they respond to any kind of intersection, right? When it comes to programming anything involving movement, such as games, kinematics, all that kind of stuff that you've kind of practiced a little bit of in AI, you need to use trigonometry to be successful. In fact, you really must know this in order for you to be successful. One thing we used to have in this course is calculus, and we don't include calculus anymore in the course content. We used to. When we were in-person learning, calculus was one of the subjects we kind of snuck in there in the first half of the semester. We've, in the meantime, we've removed it for a couple of reasons. One, I can't remember a time when, over the last little while, I've had to use calculus to create a physics system, okay? So there's something that's different here that I'm talking about. Physics and creating a physics system for a game engine. Creating a physics system is making physics work. One thing that will not be allowed for this semester is for you to download and install Box 2D in your games, okay? So you can't, kind of install Box 2D and SDL Engine and make sure that that all works. So that's something that you have to do from scratch. You can't use a built-in game engine or anything else like that, or a commercial game engine from somewhere else and make it work. Like, for example, ammo or bullet physics or whatever in your SDL engine. You can probably get that installed, but it's not something that I want you to do this semester. If you do, you'll get 0 marks for all your collision detection and response. All right, let's talk about angles. So really what an angle is, without an angle, we don't have a vector, right? And angles are kind of the basis of how you figure out what a vector is, right? So, and we're going to be talking about vectors in this course as well, a lot, I would say, right? So an angle is a way of measuring a direction, okay? And again, if two people are set off from some point, and after they both traveled 10 meters, they can be anything from 0 meters apart if they set off in the same direction, to 20 meters apart if they set off in opposite directions, right? And an angle is a measurement of how different the two directions are, right? So, and again, I'm trying to be as simple as possible when it comes to this, right? So to understand what I'm saying. All right, let's continue with angles. So since you can measure the angle in either direction, the phrase that we're going to use, which is the angle between two lines, is potentially ambiguous, right? An example is in this figure below, the counterclockwise angle between A and B, is 3/4 of the circle, right? So again, you can see that, between A and B, this counterclockwise angle, this whole angle right here. And again, if I was going to draw it, let's annotate it with a bit of a drawing here. I think I can probably draw like this. Yeah. So I mean, what I'm saying is from here to here. Wow, that's a terrible drawing. Sorry, mouse drawing. That is 3/4 of the circle, right? As an example, that's the angle. That's the counterclockwise angle between A and B, right? So a circle with various radii are marked. Okay, so let's talk about what those are. I'm just going to clear that up. What I mean by radii is from the center of the circle to the extent of the circle right here, right? You can see that there are 3 radii, okay? So we measure a radius, each radius, from the center, right, to the edge. Okay, so that's a radius. When we talk about diameter, and we're going to be talking about diameter next, we measure from the edge, from edge to edge. That is the diameter, and it usually cuts across the origin or the center point of the circle, all right? So that is the difference between diameter and radius, okay? So a diameter is equal to 2r, very good. I mentioned this, and I'm going really super slow, guys, and if you think this is really dumb, and you're like, wow, this is like baby mathematics, right? Yep, it is. It's baby mathematics that you all need to know how to do properly. And unfortunately, there's a lot of game students who don't know. And it's okay. Remember that we're in a safe learning environment, that you don't have to worry about it. I don't want you stressed about it in terms of what to know. I'm going over it again because I want everyone to understand how everything works. All right? Basics, basics. We're starting from the beginning. Okay? And it's a good review for people who've been off for the summer. All right, so that's kind of, the first thing we want to talk about. And let's continue. So generally, when we talk about angles between two lines, you mean the smallest angle, all right? And when we look at this and we use this approach, this is the approach we're going to be using in this section. Angles can be measured in different kinds of units, right? One of the units that we use is the degree. How many degrees are between one line and another line, right? As an example, what's the angle in degrees? Okay, and usually it's written like this: 1 degree. Okay, there are 360 degree or 360 equal parts in a circle, in an angle, right? And we want to figure out how many of those parts separate one line from another line. Okay, so pretty simple stuff. And here's an example about it. So when we have all of the angles connected to the origin, they all have to be adding up to 360 degrees. So 60 plus 90 plus 45 plus 30 plus 15 plus 48 and 72, they all have to equal to 360 degrees. Okay? Some common angles are measured in degrees. So one of the, a big angle that we always want to look at, and very, very common one for us, is the 90-degree angle, or what we call the right angle. Okay, this is a very important one. And also a half turn, or a straight line is what it's also called, is 180 degrees, right? So if it's a flat line that goes around, like for example from here, and by the way, in our code, a lot of times this is north, right? And this is south. A lot of times this is east, and this is west. So the compass rose that I'm drawing here, from a programming perspective is how we usually see angles. One thing to note is in your code, you might see that an angle that goes this way is actually the positive angle, where this is 0 degrees and this is 90 degrees. If I can actually draw this 90 degrees, which is terrible with this mouse. Woohoo! Right? And this is how it works. So from north to south is 180 degrees, and that's a straight line. Again, pretty simple. Let's continue. Again, the most important is the right angle. Right angles is the way that we can help us solve triangles. And one of the things that we always want to talk about is when two straight lines meet at right angles, we say that they are perpendicular. The name perpendicular always means at right angles to. Okay, so we can use perpendicular lines or right angles to the circle, right? We can draw a tangent line. We're going to talk about tangent lines in the future as an example, and we can draw a line that's perpendicular to an object. So here's an example of quadrants. Okay, this is something else we want to talk about. So quadrants, again, we're just stepping up the knowledge here slowly. We're adding more vocabulary. So, and again, to remind you of what we talk about. So typically when we look at a circle, we think about that there are 4 quadrants, okay? In this quadrant, x is positive, and this is in the Cartesian plane, mathematical Cartesian plane, and y is positive. However, I want to mention that in 2D, when we think about the 2D coordinate system, right, that in SDL, when we move to the right, when x moves to the right, it goes positive, but when x moves up the screen, it goes negative. So this is where it can be more complex to use the formula that we learn in math and apply to graphics, okay? Again, x here is negative, and in this diagram, y is positive because y is up, as an example. But most times in 2D, y is down, okay? It really depends on how you're looking at it. So there's 4 quadrants, and again, I'm not going to number them, which ones they are, but you can see that this is the positive quadrant, and down here would be the negative quadrant. And these are mixed, okay? Positive and negative, depending on where you are from an x and y perspective. Please remember the flipping of the y when it comes to drawing your stuff for physics. Okay, sometimes we want to talk about magnitudes of angles, the range, if you will. Some angles are smaller, and when an angle is smaller than something else, we call them acute, all right? Any angle that's smaller than the right angle is called an acute angle, right? Any angle that's larger, obviously, then is called an obtuse angle. Larger than a right angle. So greater than 90 degrees is obtuse. Less than 90 degrees is acute. Equal to 90 degrees is a right angle, right? An angle greater than half of a circle, so something that's greater than half the circle itself, let's say more than 180 degrees, is a reflex angle. Typically, we don't really talk about it too much, but that is the official name for it. All right. Once you know the radius, then we can start figuring out other things about a circle, right? The area of a circle is always in a proportion to the square of the radius. And one of the key values that we always want to learn is the value of pi, right? So pi is a mathematical constant that we use. The Greek symbol is pi. In Greek, we actually call it pi, not pi, right? But 3.14 is an okay approximation, Shimron, but you want to go a little bit more complex. If you're actually going to include pi in your calculations, you want to go at least something like 3.1415927. And you should remember these numbers, right? It should be part of your, kind of DNA to remember what the value of pi is. You should be able to use that value. And then we know if you want to figure out the area, then we want to multiply pi by the squared radius to figure out the area. Okay, so that's one formula that you may need if you want to find the area of a circle. okay, typically. Pi is a key value when it comes to trig as well, and we're going to see that. But pi is always measured in radians. It's not measured in degrees, and we're going to talk about that in a bit too. All right, so it also turns up in circumference. If I want to know kind of the distance around a circle, right? I want to find the distance around a circle, then I can find the circumference by multiplying pi r, so pi, which is the proportions of a circle, that's what it is, multiplied by its radius. So the bigger the radius, the bigger the number, right? Times 2, and that is your circumference, right? So 2 pi r, circumference of a circle. Twice the radius or the diameter. If you can, instead of taking the radius, if you put pi d, that's also good because that's the diameter. Radians, we talked about that just now. So again, when we measure things, we measure them in radians. And this is a challenge, guys, when you're doing calculations on the computer. Whenever you run a cosine or a sine function in math, in C++, it will accept radians. It will not accept degrees, and it could mess you up. You'll start looking at it and going, why is this giving me some wacky value? Chances are it's listening for radians and you're giving it degrees, right? And that's why it's not giving you the right value. So instead of dividing a circle into 360 equal degrees, you divide it into 2 pi radians. 2 pi radians. So, which is to say 6 and a bit of them. Okay, that's what it works out to be. And usually with the unit circle, they talk about the unit circle with a radius of 1, and that is how they like to figure out the number of radians. Okay? Let's keep going. We need to convert. A lot of times we need to convert between radians and degrees and between degrees and radians. We need to do that over and over again, right? And the reason why is because when I want to turn 60 degrees, right, as an example to the right, when you pass the orange mailbox, it's easier for us to understand degrees than for us to understand radians. It's not as intuitive for us. Instead of saying, turn 1/3 pi radians. Doesn't make any sense to me, in the real world. So in the real world, we want to convert it back to degrees. Or from degrees to radians, we want to feed it into some kind of a function, cosine or sine or tangent kind of function, a trig function. So how do we convert? We know that 1 pi radian is 180 degrees, and 1 degree is 0.0174532, whatever it is, radians, and this is the way we would convert it. Sometimes what we do is we have, in our SDL engine, we have, kind of degree, deg to rad, and rad to deg. And let me show you that. So if I was to, remember that our SDL engine is up online. So if you go to, actually it's right here, github.com/George Brown College /SDL engine. This is the link again for the one that we're using for this semester and that we used last semester. There it is. Okay, so this semester is this is what we're going to be using. And if you look at some of our source code, you can look at it right here on GitHub. And if you go into util, right? So if you go into the util folder, util.h or util.cpp, if you go to util.h, it shows you a bunch of utility functions that you get off right away. But under, if I'm not wrong, util.cpp, it actually talks about, how to convert them. And I've created some constants for you. One of them is deg to rad. So deg to rad converts from, degrees to radians. It takes the pi value from our GLM. We're using the GLM library. So GLM is a math library that we can use for OpenGL and other graphics that we're doing. We convert it to a float and we divide it by 180. All right, so that is how we get degrees to radians. And the opposite way, a radians to degrees, we take 180 and divide it by pi, basically, is what we do. So we get that value. You could create a constant here instead of doing this. So if you wanted to create a constant real number and put it here and assign it to this floating point number, you could do that, okay? It's really up to you if you want to do this calculation, but it's only done once, which is kind of a good thing. Okay, and of course we also want to calculate epsilon. So epsilon is something that is another magic number or constant that we use a lot when it comes to approximating distances. So very small numbers if they're close to each other. All right, so that's one way of doing it. So again, radians to degrees, we just talked about that. You need to convert, and you need to convert because on one hand, could I post it on Blackboard? Yes, I can. On one hand, and you'll get it anyway when you're going to be, Shimran, when you're going to be working with your assignment 1, you're going to use STL Engine anyway, and Joss is going to share that with you in labs. We need to convert because it's not intuitive for us to use radians in the real world, and we need to convert because, you know, cosine, sine, cosine, and tangent, and those kind of trigonometric functions don't understand degrees, they understand radians only. All right. I'm going to keep going. I duplicate this. So yeah, this is from convert radians to degrees and convert from degrees to radians. That's the formula. Triangles. Again, another building block. Again, trig is the area of mathematics that studies triangles. And at the same time, the triangle is also studied extensively in geometry. So both those two things, right? Without the triangle, and a triangle is a figure made up of 3 points that's not lying on a straight line. That is the definition of a triangle. And when points are positioned in this manner, they are known as non-collinear. So points that are not on the same line, non-collinear, right? Each point of the triangle is referred to as a vertex, right? And then all the vertices together, they're edges that make up the sides of the triangle. These edges, vertices and edges make up each of the triangles. The triangle itself in graphics, the edges and the vertices, there is a face or a plane that makes up the plane of the triangle when it comes to creating 3D graphics. And you'll learn about that in OpenGL. So there's 4 main types of triangles that we can talk about. But let's think about how this all works. Usually what you have is you have an angle and ABC. When we look at an angle ABC, we're looking at the angle beta. The angles are denoted in Greek letters, alpha, beta, gamma. The edges are denoted in small letters, A, B, C. The vertices are denoted in capital letters, capital A, capital B, capital C. Okay, so if I say edge A, right, this is the A that I'm looking for. Okay, if I say angle alpha, it's this angle right here. Okay. Sometimes we also use other letters and numbers and other marks to denote that the triangle is the same size. Some edge is the same size. One thing to note when it comes to solving a triangle, that the internal angles of the triangle must add up to 180 degrees. Okay, so when you add these 3 angles together, alpha, beta, gamma, they all add up to 180 degrees. And this is a way of figuring out or solving the triangle. Okay? And we just say that here. So one demonstration of this is how if these angles are the same, these are also similar angles. You can see that this angle here, beta, is the same as this angle up here, beta. This angle alpha is the same as this angle alpha. And this angle gamma is the same as this angle gamma. If you add up alpha, beta, and gamma, they make up 180 degrees. And therefore, alpha, beta, and gamma in these triangles all add up to 180 degrees. And this is kind of a way of figuring that out. Yeah. Okay. Again, very, very simple. Again, I'm going slow. Forgive me for those people who know this the theory and all that kind of stuff. I'm doing it because I want you guys to be on track and have the foundational knowledge you need to do everything else in physics. All right, so we talked about different kinds of triangles. So here's one, an equilateral triangle, where all of the angles are equal and all of the edges are equal in this case. They must be equal, an equilateral triangle. In this case, when you have all angles the same, they must equate to 180 degrees. So if you take 180 divided by 3 possible angles in a triangle, they must be 60 degrees each. That's an equilateral triangle. The other one is an isosceles triangle, where two edges are the same. And this means that there are two angles, this one and this one, that are the same, right? But this angle up here is going to be whatever it is, depending on what these two angles are, okay? And the other one is a scalene triangle, right? Where they have no edges, sides, or angles that are equal, a scalene triangle. Okay. There are relationships between these types of angles, and we'll talk about them later. Right angles. We talked about right angles as being perpendicular, but right angles are kind of the key, if you will, to solving physics equations, right? So the way it works is that when we have a right angle triangle, and again, you can take an angle, any triangle actually, and divide it in two. Sometimes you'll get two triangles that are right angle triangles from a triangle that is a scalene triangle, as an example. So again, if I go back to this triangle here, no angles are the same. And if I was to chop the triangle in half, so if I took the base of the triangle, this is usually called the base of the triangle, and I took the tip or the top of the triangle, and I was to divide this triangle in half, like this, what I would produce is two smaller triangles, right? One triangle over here with a 90-degree angle. Let's see if I can do this with my tools. So here's a one right angle triangle here, and obviously on the other side, there is another right angle triangle on the other side as well, all right? So those two right angle triangles are easier to solve, right, than the scalene triangle on its own. I want to break the problem down into smaller chunks where I take the triangle and divide it by 2. Sometimes the most difficult challenge in this case is figuring out the height of the triangle, this part right here. Once you know the height of the triangle from the base to this vertex up here, you can pretty much figure out what the angles are if you know the length of this side and the length of this side. All right. Actually, if you know these two sides, you can figure out the other one. We're going to start talking about Pythagorean theorem in a bit. All right, let's continue. So we talked about right triangles, and right triangles, we have a figure that has two legs. Let me skip back one. Special names for the sides of the right triangle. So two of the sides are called legs, and the other one is called a hypotenuse. Hypotenuse. And usually that's the side that's opposite from the right angle. So example, these are called legs. A and B, these two sides are called legs, right? And the side that is opposite from the right angle is the hypotenuse. That's what it's called. Okay, and so these two legs join the hypotenuse to create your right angle triangle. You know that this is 90 degrees. So therefore, alpha, whatever that is, and beta, whatever that is, must also equal to 90 degrees. And this is where, again, what we're doing with different theorems that we're going to be using is we're breaking down the problem into smaller chunks to understand how to solve a triangle. Here's a famous guy, this Greek mathematician. Shimron just talked about it in chat. He said it's Pythagorean theorem. Pythagoras, again, he was kind of around from 569 to 494 BCE. Notice that the dates are backwards. And the reason for this is because as we approach, kind of a zero, we start off, this is before the Common Era. That's what BCE stands for. And he developed a famous theorem called the Pythagorean theorem. And it's kind of a thought, or, kind of a, he had a hypothesis, all right? And really, at the end of the day, when we think about the Pythagorean theorem, it gives us a proportion. We're given some information, right? We can use the Pythagorean theorem to solve a triangle. That's really what it's for, okay? So again, I just did this. Notice that this is exactly the case here. I split this off. So the way it works is with right-angled triangles every single time. You can't use Pythagorean theorem with triangles that are not right-angled. So what you need to do is you need to take a triangle that has no right angle, create two smaller triangles, and then from there solve each side. So for example, I would solve two of these triangles to solve the bigger one. Okay, that's how I would do it. So again, there's some really important things. So the first thing is that right angles, or they appear in many natural circumstances. And the second reason is that right angle triangles is that they have a number of useful properties, which we're going to discuss, right? And the third reason is that any triangle can be easily split into two right angle triangles by dropping a perpendicular line from the vertex, one of the vertices at the top, to the base, like we talked about before. As mentioned already, right-angled triangles, studied by Pythagoras, right? And the Pythagorean states simply that C is equal to the square root of a squared plus b squared. So that means if I look at an angle C in a right angle, right? Let's suppose that I want to know that the hypotenuse is C. Then C is equal to the square root of a squared plus b squared. Okay, C being the hypotenuse. Problem with using Pythagorean theorem to solve the distance, because think about what we're doing, we can do with right angles, right? If I go back to that right angle diagram, and let's suppose I have a vector that goes from A to B, right? Or from B to A. I want to know the distance or the magnitude of my vector. In pixels, I can calculate the distance from the origin, right? And I can say I have to march across X number of pixels to get to B on the X-axis, and X number of pixels to get to A on the X-axis, on the Y-axis, right? And then I can figure out the distance in pixels, or any unit you want, from A to B, right? And the way to do that is to say that the distance, the magnitude, C, would be the values on the x-axis squared plus the values of the y-axis squared, and take the square root of that. And what that gives us is a mathematical way of getting the distance between 2 points. The challenge that we've talked about in the past is that every frame is computationally expensive. We don't want to do this every frame. If we're doing something like this, calculating the distance between 2 points every single frame, that's a bad thing. And in fact, what we can do instead is use squared distance, where we don't take the square root. Correct. Ethan. So again, an infinite number of right-angled triangles with different values. But one thing we know is that there are some magic triangles. Whenever I talk to my son and I talk about some magic numbers, there's some magic numbers, or what we call triples. And usually how they go is this, some things to remember. The 3, 4, 5 triangle is a very common triangle. 3 meaning the length of this side is 3 units. This is 4 units, then this must be 5 units. 3, 4, 5, okay? With the right angle being between the 3 and the 4. Okay, so common triples. And there's a bunch of them that we have here. They're called Pythagorean triples that occur naturally. And what we want to try and do is remember some of them. One of the common ones that I like to remember is 1, 1, root 2. It's not really listed here. That's another common triple, right? 3, 4, 5, 5, 12, 13, 7, 24, 25, and so on. These are the ones that kind of are very common that we see all the time, okay? Especially the first three, 3, 4, 5, 5, 12, 13, and 7, 24, 25, even up to here. I would say that I've seen a lot of this over the time. So why? Why is it important to remember this? Especially 3, 4, 5. 3, 4, 5 and 1 root 2 is kind of like the main ones we want to remember. Why? Because when we think about it, we know what they equate to. That means we automatically know the length of the sides. And if we know the length of the sides, then I can figure out the rest. The more information we have when we solve a triangle, then it's easier for me to solve it. So here's an example. Here's 1, 1 root 2, like I mentioned before. For 1, 1 root 2, that's another one. 1, 2 root 3, that's a great one. Is both angles must be 45 degrees in 1, 1 root 2. Again, these are proportions. It doesn't have to be exactly 1 unit. If this was 2, 2, 2 root 2, it'd be the same, right? 1, 2 root 3, if they're the same proportions were here, for example, if this was 3 and if this was 6, right, and this was 3 root 3, again, you'd have a 1, 2 root 3 triangle, and you'd have a 60-degree angle here between the 1 and the 2, and a 30-degree angle between the 2 and the 3. Notice that every one of these triples are right-angled triangles. So special triangles, magic triangles is what we call them. 1, 1 root 2, 1, 2 root 3, 3, 4, 5 triangles. They're very common. Try and remember at least those. Okay? Let's continue. So trig functions. Once we start talking about, trying to figure out the angles and trying to solve the triangle itself, all the numbers that belong to the triangle, including the angles between two edges or two legs, if you will. So edges, the angles here between the hypotenuse and this leg and the hypotenuse and this leg of the right angle triangle. What we want to do is we use something called a gradient or the slope of the line. Slopes are great for 2D, but they don't really work great for 3D. And a lot of times you can get away with not using this. But usually, typically what we say is the slope, so the slope of the line is usually A over B, or rise over run. That's kind of some old terminology. But run is usually associated with X, and rise is usually associated with Y, right? So rise over run or Y over X. It gives you the slope of the line, okay? And you're going to see this relationship, Y over X, to figure out the slope of the line is a very common way when we use trigonometry. So trig functions that we're going to start thinking about are sine, cosine, and tangent. And what they do is they give us proportions, right? Where we have a relationship between one type of function and another, right? So for any right-angled triangle with a leg parallel to the y-axis, so that means it's on the y-axis, up and down, and a leg parallel to the x-axis, so that means it's axis-aligned. That's what we're talking about it. The gradient or slope is always A over B, where A is the angle of the edge or the leg that is on the y-axis, parallel to the y-axis, and B is the leg that is parallel to the x-axis. Okay? When we think about this relationship, we can say that the size of the angles at A and B, so that means if I go back to that right angle triangle, this one, the size of the angles here and here, that's what it's talking about, right? I'm going to skip back to this. You can use tangent, the tan function, to figure these out, all right? And respectively, what we can say is there's a relationship between tangent, the tangent function and the trigonometric function, and sine and cosine. One thing to note, guys, whenever we talk in physics, for the most part, whenever we talk about sine, typically we're discussing the y-axis. If I break down the triangle into two components, the y component and the x component, and I want to figure it out, example, the velocity of a bullet that's traveling across a vector, typically what I want to do is I want to break the component down in sine and cosine. Sine relates to y, and cosine typically relates to x, the x-axis, right? And it's a proportion of the angle, the forces that travel across the vector. And we're going to be talking about that again in future lectures. So the abbreviation for tangent function is tan, and for cosine is cos, and for sine function is sine. And what do these things look like? Well, we can use a online tool that I've shared with you online on Blackboard called Desmos. Let's do that together. So if I look at Desmos, I look it up. It's a free online tool, right? And what you can do is you want to see the graphing calculator that's included. You get this line right here, and you can start making a relationship between, x and y, right? So for example, you can say something like, y is equal to x, right? And then if you do, you get a line that looks like this. It automatically graphs this out. For your assignments, I'm going to be asking you to graph out y is equal to x and other kind of function like this. This is a linear function. Y is equal to x. What about if I said y is equal to x plus 1? Well, what that does, whenever we add something to x, if I make a relationship between y and x and I add 1 to x, it actually moves the line back from the origin. See, the origin is right here, right? And I moved it back this way, right? I moved it negative to the negative side of the y-axis, okay? If I was to subtract x, to subtract 1, then it would move to the other side of the y-axis. So again, very simple calculations. Try this out, guys, online, right? So this is interesting. What about if you said something like x squared? By the way, to do squared functions, just use the caret. So the symbol underneath the 6. So x squared, right? There is the x squared function. Okay, so that's x squared. And you can see that this is a parabolic function, right? And it looks like it goes goes down and goes back up. What if I wanted to flip this function around? What would I do? If I wanted to flip this function across the x-axis, what would I do? How could I flip this function? What formula would I use here, do you think? So Phil says root it. Okay, so that means if I was to use a square root, right? And so if I try doing a square root here of x squared, you can do that by typing in like so. You can say square root here in Desmos, open up a bracket, and then do x, and then this. This is what the square root would look like, right? Is that what you wanted, Philip? That's not exactly, what you're looking for. It's still, has the same shape. It's just not, a parabola anymore, right? So again, what about if I was to go back? So let's get rid of the square root. So x, again, x squared. And what we want to say is if I put a negative here and here, then it flips it around. But this is very interesting, right? If I want to flip an animation, I can flip it across the x-axis or I can flip it across the y-axis, right? I can do that. Okay, similarly, what if I wanted to flip a line? So I've got this line that goes this way. What if I put the minus in the front of it? So I said, okay, I want to put a minus here. It flips it the other way around. It kind of reverses the line, right? So it flips it, okay? And it flips it across. How did I get that? So what does it really do? If you look at this portion of the line, and by the way, you can put extents to this as well. Desmos has a quite extensive, kind of thing where x must be greater than 0, right? So if x is greater than 0, how do I do that? So I say, so x must be greater than 0. Okay, if I did that, that's all of this, which is really kind of cool. Desmos does all this thing for you, right? That's where x is greater than 0. And if I said y is greater than 0, because you can put these constraints, then that's all this portion. Y is greater than 0 and x is greater than 0. What if I wanted to do both, where y and x is greater than 0? Can I do that in Desmos, right? So if I say y and x is greater than 0, does it compute? Can I put the and symbol in there? How do I do that mathematically? Do I put in the comma? Think about this, right? So if y is greater than 0 and x is greater than 0, y is greater than 0, that works. And then x is greater than 0, does that work, right? How do I do it? And so there's some things that you can do here. One thing you can do with Desmos is you can add in a bunch of them, a bunch of expressions, right? You can add in a table or an image in the background and a bunch of other stuff, right? So if we look at an expression, you can add in whatever you want in there. And there's some good hints and help on how to add more complex expressions in Desmos. Okay, so here's some examples. If you open this up, it gives you some examples for, let's see, the unit circle, right? Here's the unit circle. Let's open that graph. And you can see what it does here. So here's a couple of things. X squared plus y squared is equal to 1, right? Cos A and sine of A, right? And then where A is equal to 30, you can change this value, right? So you can figure out different things. Lots of really cool control here. And there's that square brackets where, here's what I was talking about before, these curly braces that say 0 is less than x is less than cos of A, and so on. And that gives you y, and it kind of creates different parts of the circle. All right, so kind of really, really cool stuff. And you can see that I can keep some of it or none of it, right? So this doesn't do much unless I use it. So if I say something like, let's make an expression, and I say A, plus 5, or if I say x, if it's x plus 5, and I say the value of x starts off at 155, then I can start figuring out, different values, right? Where here's take a look at that. So I can actually, here's x, and I can actually figure out the size. I can also zoom out, guys, which is a really cool thing. And you can see how this all works together. So very, very nice. Okay, so that's trigonometry with Desmos. And there's a lot of examples here. You can also go with a new blank graph and start over again. So I'm showing you this because it's an interesting graphing tool that's free to use, and you may use it for your assignments. All right, let's get back to this. So we talked about the trigonometric functions, cos, sine, cosine, and tangent. What happens if I post that in here? So cos of x, what happens? Well, we get cosine. So one interesting way of figuring out cosine, right, as an example, is that cosine starts positive. So 0, when cosine is, when x is 0, y is 1 all the time with cosine. So that's one way of remembering it, right? And when x is 0, right, as an example, so x here will be 0, then that's where it intersects. So it goes here like this, and then there's when x is 0, then y is 1. When y is 0, x is right here as well, right? Y is 0. Whereas if we talked about sine, so if I did something like sine of x, right? There's what sine looks like. Sine starts at the origin 0, 0, and it goes pi over 2 here, where y is 1, right? X is pi over 2, right? Or half pi. And then it goes a full pi. So this is a whole kind of half circle. This is 180 degrees then, if you think about it. That's what this describes. And this describes the other 180 degrees. So this whole cycle right here, if we were going to say that where x is equal to, is greater than 0, and I think you do that with a comma again. x is greater than 0, right? And maybe, is it a comma? I forget. There's a way of doing it. The notation is what I'm talking about. And I think if I was to look at one of these things, which was the circle graph, then it is square brackets. So yeah, like this. I think you have to do both sides, right? But that's what you can do. So you can say something like x is greater than, so 0 is less than x and less than 1. And you can see that's a small area of your graph, right? And so kind of interesting stuff that you can see, right, when it comes to this kind of thing. Okay. Does that make sense? So we want to look at sine then, and the relationship with sine to x. It starts off here at the origin, and then it goes up. Whereas if I look at cosine, whenever you remember sine and cosine doesn't start at the origin. It starts up 1 up from the origin, right? And that's the only difference between sine and cosine. It's kind of shifted, if you will. And again, to visualize this, just put both together, like so. By the way, if you go here, you can show or hide different elements, right? And there's a lot of other control you have here as well. You can see the grid lines as an example. I can add a label for the x-axis. So let's say, for example, I want it to go from 0. So start off at 0 and is less than x is less than 10. And I can also add in steps of 2 or 3 or 4 or whatever it's going to be. So 4. So every 4 you want to use your graph to map that out. You can do that here. And you can also choose radians or degrees. There's a lot of stuff you can do for this. Okay. That's Desmos. I'm not going to go too much more into it. I think it's one thing for you guys to explore. All right, so here's some trigonometric identities, right? And once we have trigonometric identities, or trig identities for short, then we can start figuring things out and it'll help us solve kind of some problems when it comes to triangles. I want to solve the triangle. So we know that the sine squared of x plus the cos squared of x is equal to 1. That is a trig identity, right? And by the way, there's also a shorthand. Whenever we say sine squared x is like saying sine x all squared. Same thing. So whenever you see this, don't be confused by it. It's just a shorthand notation for this. Okay. Here's some other ones. Sine x plus y is equal to sine x cos y plus cos x sine y. And so on. So some trig identities. Now, in the past, when we were doing calculus, we also did a bit of trig because, sometimes we want to again, use one to help us solve the other. Here, I'm not going to go into much more detail than this. I've just listed these as common trig identities. Sometimes we use trigonometry like this to validate, as an example, to validate what we're thinking and to prove that the angle we're looking at makes sense. There's also inverse trigonometric functions, and usually we use arctangent, arccosine, and arcsine, and they're written as a sine, a cos, and a tan. Okay, so that's kind of the way it works out. Okay, sine to the -1, absolutely, Nicholas, and those kind of things. So we also have some triangles. We want to solve a triangle, and we know that there's proportions for each of the triangles, right, as an example. And what we can do is we can use the sine rule to help us solve the triangle. And we only have partial information. We know that there's a relationship for A over sine alpha and B, remember this is the side, B over sine beta and c over sine gamma. We know that these things are all the same because they're proportions, right? So if we're given the length of side A and an angle, and I want to find the length of side B and that angle, when we know that sine C is, the angle of sine C is 90 degrees, we can figure out the one that's missing based on the information that we have. Okay, typically that's what we do. All right. The cosine rule is slightly different. It's what it does is part of it looks like the Pythagorean theorem, but we also subtract 2bc cos alpha, right? And so when we use this when we don't quite see the information we need, right? So there's missing information, and part of the missing information is that's not allowing us to make a relationship between one side and another side, and so we would use either the sine rule or the cosine rule. When we want to figure out the area of a triangle, and again, this is all just basic stuff, guys. We're just talking about naming conventions and vocabulary here when we're talking, right? So depending on which measurements we know, there's a lot of different ways to measure the area of a triangle. Okay, so one of them is we know that a triangle, the total area of the rectangle, right, is twice the area of the triangle ABC, right? So you can say that the area of a triangle then is half base times height. Half base times height. Okay, typically that's how we can figure out the area of a triangle. SOHCAHTOA, or SOHCAHTOA, like the way I like to remember it. SOHCAHTOA is a relationship. We can say that if we know some information about a triangle, right, as an example, right, and then we want to make a relationship. Example, let's say we have the opposite angle. Typically, this opposite angle means opposite of the angle we're looking for. So if this is the angle that we're looking for, sine of x, we want to find the angle, then we know that the opposite side of the angle right here is opposite of this angle. This side is opposite, we can say. The side that's adjacent is this side. This is the adjacent side, right? And this is the hypotenuse. So what we can say is the sine is equal to opposite over hypotenuse, or so, this part, right? And that means that sine of x is equal to the relationship between the opposite side over the length of the hypotenuse. That gives us a relationship, and we know that the angle that we're going to get here is the same relationship. In order for us to get the actual angle, we need to get the arc sine of whatever this relationship is, of opposite over the hypotenuse. Okay? And the same thing goes with ka and toa. If we're given, if we know we want to try and figure out angle x, and we know that we know the adjacent angle, we know the hypotenuse, but we don't know the opposite side, adjacent side and hypotenuse side. We don't know this one. We want to figure this one out. We can use ka, or cosine is equal to adjacent over hypotenuse. And then the last one is tangent. We know the opposite side, and we also know the adjacent side, but we don't know the hypotenuse. We could use the tangent relationship. So the angle, there's a relationship between this, and we want to figure out opposite over adjacent. However, in this case, if we know two sides, we can figure out the third side always by using Pythagorean theorem as well. Keep that in mind. So in other words, if I know, in this case for tangent, if I know the opposite and I know the adjacent, I could simply say that hypotenuse is the square root of the opposite squared plus the adjacent squared, right? Which is the same thing as doing it here, but here it's just a quicker calculation to use the tangent and use arctangent as a function that's built into C++. Arctan2 actually is what you'd use. All right, let's do some examples. So let's graph the following function by plotting points. And we can confirm with Desmos. If I was to plot this function by hand, which is kind of what I'm asking you to do here, let's do it by using our tools that are built into our here inside of PowerPoint. So again, let's draw. The first thing we do is whenever we draw something, whenever we plot points, we draw the axes, right? So here are the axes. There's the x-axis, and we would label them, right? In math, we would start labeling these things. And by the way, to label stuff, kind of wherever we want, we can use text boxes. So this would be the x-axis, let's just say, right? We can label it the way we want. And we can also copy paste in PowerPoint whenever you're doing a presentation or some kind of thing. We can change this to whatever we want. So x and y, right? So that's the first thing we would do. We plot x and we plot y. When I want to start plotting points by hand, when I want to plot point by hand, I want to start replacing values of x. So in other words, the function f of x, we can think about this as y, right? This part is y. We want to make a relationship between y and x. So when x is 0, that's the first thing that I would try. I would replace x with 0. And in fact, what you could do is make a small table, all right? You can make a small table. Let's see if we can insert a small table, all right? So we're going to make it so that it is like a couple of columns, right? And we want to insert this table here, right? And let's see if we can do it down here. So there's a table. And we want to say that this is values of x and this is values of y. And we can start plotting this out. This is what I would do if I was plotting it by hand, right? Because at the end of the day, what you want to think about is, what the values are for each thing. Once I have a graph or table like this, I can start mapping out. Let's see if I can undo this. I can start mapping out what my values are. Let's split the table over here. Okay, and let's add a couple more. I can kind of insert additional cells. I just want to add additional fields without drawing it. Anyways, doesn't matter. Let's just use these. That's fine. Along the top bar, sure. Oh, you mean up here? Top drop, the pop-up. Top pop-up. Yeah. There we go. I can definitely draw it, but I want to add an additional, basically make this basic. Let's see if I can change the value. These are just changing the way it looks, the borders and such. And I wanted to make it so that the borders are like so we can see it. There we go. All right, so let's say where x is 0, and let's do this. We'll kind of do one of these. I want to kind of make these aligned so that they are like so. Where x is 0, then what's y in this case? If x is 0, what's y? That's the first thing I would do. Okay. So if I substitute 0 for x, then y would be -4. Okay, that's the first thing. So again, what you could do is you could start separating the lines here in your graph, right? To start thinking about where all the lines are without using a graph. Again, I'm just going to use my eye to create the separations. If I was going to draw this by hand without a ruler, as an example, I probably would do the same thing. So maybe I'm going to put a few points on the graph here, and the same thing goes in the other way around. I'm probably going to insert a few points here or parts of the graph. These lines represent the points of the graph, right, where I'm going to start drawing my points to start mapping up this function, okay? And again, we can use Desmos to confirm, but this is the kind of exercise that we can do, all right? So when x is 0, then y is -4. So we need one more line where this is y. So this is where when x is 0, y is -4, and you can insert different kinds of shapes. Let's go back to home, and I want to go to circle, and let's see if I can insert a circle that looks like this without, make it a little bigger maybe so I can access it. That's too big, and let's make it smaller. PowerPoint. There we go. This is your first point. It's massive, but it's okay. So this is the first point. So where y is 0, so x is 0, y is -4. Here's the other one. What happens when y is 0? When y is 0, what's x? How can I do that? I want the intercepts is what I'm looking at first, right? When I start thinking about a graph like this, I can do that. It's more difficult because then I got to solve for x, right? And I need to factor the equation, right? So that's something I could start doing. I can start factoring the equation and solve for x, right? And how do I solve for x? When we look at algebra for this equation, how do I solve for x? How do I do that? Is there a way to solve for x or factor out the equation? Well, I could do some stuff. I could move the 4 to the other side. So I could say x squared plus 4x is equal to 4, right? I could do that, right? And then what I can do is I can factor out the x and do a bunch of other shenanigans to make sure that we get x is equal to something, whatever x is equal to, okay? But here we don't need to do that. We can just plug in other values of x. So where x is 1, what is y, right? So we're going to say when x is 1, this is 1 squared, which is 1, plus 4 is 5, minus 4 is 1. So when x is 1, y is 1. So that means that this circle here, let's copy paste, and that's the next value. That's here. Okay? So where x is 1, y is 1. Do you see that I did there? All I did was substitute 1 where x is. And then I used basic addition and subtraction to figure this out. So 1 squared is 1 plus 4 times 1, which is 4. So 1 plus 4 is 5, minus 4 is 1. What about when x is 2, right? So again, a few points here when x is 2. X is 2. 2 squared is 4, plus 2 times 4 is 8. 4 and 8 is 12, minus 4 is 8, right? So that would be way up here somewhere. So when x is 2, y is 8. Let's see if this computes on Desmos, right? So again, let's bring that up. And we can bring up that same formula, this one, x squared plus 4x minus 4. So again, you'd write it like this, x caret, I can type in the caret, x squared, and you kind of space over, plus 4x minus 4. And then you can see that this part, we have the same values. Here's 0 and minus 4. We can see that when x is 1, then y is 1. That's what we want to see. So is this correct? Did I do this right? X squared plus 4x minus 4, yeah. This is the equation. Did it work? And you can see that the y-intercept here is 0.828. Okay? What about when x is 2? Then y should be 8. Let's make sure that that's true. So when x is 2, y is 8. Right? You can kind of go up here like this and actually kind of do that. So when x is 2, y is 8. When x is 1, right? Y is 1. Look at that. It's on the line. So those are all good values. And you can skim across here with Desmos to confirm. Make sense? So this is the way to do it, plotting it by hand, and you can also confirm with Desmos. How about the next one? So there's a couple of practice examples to get you guys going, right? How do I plot this one now? Is there an easy way to plot this out, right? As an example, well, minus 2x plus 3 squared plus 5. One thing to note is you need to know order of operations. Let's take this graph over here and the elements that we have here, so we don't have to redraw them. And let's pass this over to this one over here, okay? Just to do the same exercise. So we'll get rid of these points, actually undo. We'll move these points around. Okay, so what about when x is 0, for example, 2? When x is 0, that means 0 plus 3 is still 3. Remember, order of operations is bed mass. Brackets, everything in the brackets first. Exponents, right? Division, multiplication, addition, and subtraction. We need to follow bed mass, right? So again, I'm just going to go to home and type that in to remember this. Bed mass, order of operations. All of you should know this because without this, you can't do proper calculations inside of programming as well, right? So bed mass, pretty simple. So then we know that when x is 0, then this is 3. And then now we do exponent. Okay, we don't do the multiplication first. We do the exponent first. So 3 squared is 9. 9 times minus 2 is negative 18 plus 5. Negative 18 plus 5 is negative 13. So our calculations are that this is negative 13. Okay, what about when x is 1? 1 plus 3 is 4. 4 squared is 16. Minus 2 times 16 is negative 32 plus 5. And that would be minus 28. Right? And what about when x is 2? 2 plus 3 is 5. 5 squared is 25. Negative 2 times 25 is minus 50. Plus 5 is minus 45. Do you see that? All right, so those are the numbers. Now, obviously, plotting these, we would need a different scale where these numbers here, because we're starting off at like negative 13 and negative 28, our scale here would mean different things. Let's suppose that instead of these being equal to 1, that they were equal to something like, because our negative 45 is quite large, let's say they're equal to 10, okay? And we can make approximate values. Obviously, it's not going to be accurate, but if we were to do that, all right, so where x, on the x-axis, you can have different scales, by the way. On the x-axis, it can be 1, 2, 3, 0, 1, 2, 3. But on the y-axis, it can be a compressed y-axis where these are 5, 10, 15, 20 or so, or 10, 20, 30, 40, right? So we're going to do all negative numbers down here. So when x is 0, which is right here, then y is minus 13. And if each of these was 10, it'd be something like here, approximately, okay? And where x is 1, y is minus 28, 10, 20, 30. So the next point will be something like down here, right? And y is 1, so that would be over here, or x is 1. So something that looks like that. And then where x is 2, then y is minus 45, so that'd be something like here. And you can see it's kind of a linear kind of drop off like this. You can also try values that are on the other side of the y-axis, and to add additional detail. For example, what happens if where x is minus 1, right? If that was one of the values we wanted to use. So minus 1 plus 3, that would be a 2. 2 squared is 4. 4 times minus 2 is negative 8. Plus 5 is a negative 3. Right? So when x is negative 1, y is negative 3. Right? So that means it would be like right close to the x-axis. Like so. So it's something like this. And you can see that it's kind of a curve this way. And what about if it's where x is minus 2? So x is minus 2. Minus 2 plus 3 is a 1. 1 squared is 1. 1 times a negative 2 is a negative 2. Negative 2 plus 5 is positive 3. So the next one, when x is negative 2, y is positive 3. So that means somewhere like here. Again, very smart, very close to the x-axis, something that looks like this. Let's confirm this with Desmos, right? So again, instead of this equation, let's use this equation. So we'll write it the same way. So minus 2 in brackets, and then what you want to do is x plus 3, and then you want to take that whole thing to the squared. So there you are. There's that value. And remember what we do when we add 5, right? When we say plus 5, then we just put it up there, and it looks exactly like we thought it would look. Right? So there's that minus 45, right? When x is 0, let's see what happens. When x is 0, then y is minus 13. We got that value. And when x is 1, we can kind of drag along this line, right? I'm just going right there to 1. Then it's minus, like we said, 26. Let's see if we're right. Minus 28, yeah. I may have miscalculated, maybe not. Minus 27, I made a mistake. See? There you go, right? And then keep going to y is equal to x is equal to 2, right? There we go. Minus 45 was correct somehow, right? So there you go. And then the other side, when x is equal to 1, minus 1. So x, can x even go to negative 1? Yes, it can, because it can go to right. I want to show you this, minus 1 right here. Then y is minus 3. And when it's minus 2, it's not quite at the top, but you can see that we got a shape of what we're looking at here. This is just wrong. This is minus 27. So that's how we confirm with Desmos. So what did I do wrong? So I said that this is 1. 1 plus 3 is 4. 4 squared is 16. Minus 32 plus 5. Yeah, I just made a miscalculation in my head. All right, so that's how you can do it. And I'll leave the last one for you guys, the last couple to practice for you. So find the measures of each marked angle at the figure. If I know that this is 2x and this is 3x, right, then what is this angle? We know that this is a right angle, right? And if the proportions of this one to this one is 3 times x compared to 2 times x, then we should be able to find the proportions here. Same thing with this one. If there's 2x compared to 7x, a ratio of 2 to 7, we know that this whole thing equates to 180 degrees. We know that this whole thing equals to 90 degrees. So what's the ratio of these two angles, as an example, if we know that it's 2 to 3? Okay, so that's kind of a simple way of thinking about it. Supplementary angles. Find sine, cosine, and tangent. These some examples or practice for you. Okay, I ask you to do this. So sine, cosine, and tangent, right? For angles alpha, beta. For angles alpha and beta. So what's the sine of alpha? What's the sine of beta? What's the tangent of alpha? What's the tangent of beta? What's, the cosine of alpha? What's the sine of beta? And so on. Find all that information. Okay? And solve it. In other words, instead of you trying to to plug in the values, what could these two values mean? What would you use here to figure that out? Okay? Well, you can use SOHCAHTOA for that, couldn't you? Right? Because you have all the sides. You have all the sides figured out, and you have this right angle. You can figure out these two angles with SOHCAHTOA. Okay? Solving right angle triangle, give it two sides. So I've given this side and this side. What can I use to figure out this side? Right? What's c squared? I can use Pythagorean theorem for this one. Right? And find the length of a given angle of an elevation. Okay, so sometimes you get like weird problems in physics where it sounds like this. The angle of elevation, the angle of elevation from a point on the ground 15.5 meters from the base of a tree. People are like, what the heck is this? What is he talking about? Guys, number one thing to do whenever you're giving a problem like this, and this is kind of, I'm going through this with you so you get a sense of how this works, and it's pretty simple, is start drawing. That's what I recommend. Start drawing the angle, the triangle, right? So let's use the tools we got. All right, so an angle of elevation from the point on the ground, 15.5 meters from the base of a tree. Let's draw the tree. Let's suppose we have a tree that's like this. This is the tree, right? The base of the tree, right? So we want to say 15.5 meters. So we kind of connect the base of the tree this way, and we label it. Okay, we kind of add a label to this, that we can say that this is 15.5 meters. Okay? How did I get that? If this is the tree, we're 15.5 meters away from the tree. That means this point right here is 15.5 meters. The base area, the top of the tree to the top of the tree, so the point of elevation from the base of the tree to the top of the tree, this angle right here is what it's saying, right, is 60.4 degrees. Find the height of the tree. So what this means is erg. Can I do it? Maybe not. And I mean, these tools are kind of primitive, but whatever, right? You know what I'm talking about. There we go. So this angle here, this angle here is, you know what I'm trying to do here, right? I could have drawn that by hand too. Let's just draw it by hand. Instead of doing that, I'll just do, I wonder if this works a little better. Okay, yeah, that works better. So it goes like this. So take this one and, sorry, typically I use another tool, but my tool is not seemingly available right now. There we go. So this angle here, if we would label it, we would go to here and we would say this is 60.4 degrees, 60.4, right? So if we know that this angle is 60.4 and we have this, how do we find this? Well, we draw a triangle, right? So we say that this triangle here, right, to here, this is the elevation. Now this is tricky, right? Is this the angle we're looking for or the angle of elevation? What's the angle of elevation? Is this the angle of elevation or is this the angle of elevation? Well, we know that this can't be 60.4 degrees. It's this, right? It's 60.4 degrees. Why? Because this, my friends, is a right angle triangle because the base of the triangle. So actually, drawing it correctly, this would be 60.4 degrees and this would be your right angle. So now we have a right angle triangle with two pieces of information, right? But actually, we know that we know more than this, right? We know that this is 90 degrees. We know that this is 60.4 degrees. Then what must this be? What must this be up here if we know these two? Anybody? 29.6. Very good. Why? Because these three angles must add up to 180 degrees. So again, we'll put in, sorry, I got to do it right. So 29.6, right, in here. And we'll just make sure that these are smaller so that they fit inside of our angles. So this, we know these two things. So 29.6, and this is 60.4, because that's what it says. Base of a tree, so the angle of elevation from a point on the ground, from this point right here. So let's label this point A. Again, we draw everything we know, right? So this point A, capital A, and this point is B. Let's use that. We could also draw AB, doesn't matter. However you draw it, it's okay. And this would be C then. And once we have these values, right, we put these values in place, right? I'm just using a clockwise labeling, A, B, C. Let's say as an example where A is at the apex and B and C are this angle. So this line BC, we know it's 15.5 meters away from the tree. This is the tree. We're looking for this angle. We know this, and we're looking for this, right? We're looking for this. So this is what? This is the opposite, right? So let's put that in there. So we know this is the opposite. We don't know the hypotenuse, but it'd be nice to know what the hypotenuse is somehow, right? If we knew the hypotenuse, then it'd be easy, right? If we want to find this, we know that there's an adjacent angle. We know that there's the hypotenuse. We'd use cos, right? The cosine of the adjacent over the hypotenuse is equal to the opposite. That's what we want to find. This side is what we're looking for, right? So again, I'm giving you hints on how to solve this problem. So there's hypotenuse. These are the things we know. Okay? Could we figure out other things from the information that we have, right? We know that there's relationships, my friends. We know that there's relationships, okay? So we have this angle, we have this angle too, because these three angles are things that we know, right? We know we have this. Look, we have the opposite side, right, to this angle here is this. We have a relationship here, right? So therefore, if we had this relationship, we could use the formula that's up here. We can use SOHCAHTOA in this way, right? Or we can say that this is the opposite, right? Opposite of this angle here. This is the hypotenuse, that doesn't change. And this is the adjacent, right? We don't know the adjacent, but we want to find it, right? So we could say that this is the adjacent angle. And I'm just going to use lowercase a and lowercase o for this one. So we know what this is. This is the opposite, and this is the adjacent, right? And what I want to find, I have the angles, right? I want to find this. I have this opposite, but I don't have hypotenuse, okay? So again, these are things that you could also, you can think of it in this way as well, other things, right? We have one side. Okay, Andre says you can use alpha over sine alpha for a hypotenuse, if I'm right, and it's 15.5 over sine of 29.6, which is 15.5. Tan A, Samuel says use tan A is equal to opposite over adjacent. You could. Opposite over adjacent. But we don't have adjacent, but we do have, if I say tan of A, let's look at that SOHCAHTOA stuff that we were given earlier to try and puzzle this out, right? So let's take a look here. So I'm just going to go to that SOHCAHTOA. There it is. So again, given these things, these are the relationships, okay? We have this. If we have this, we can figure out this. But we need to know the other two things. If we know the sides, we can figure out the angles. This is when we know the sides. I know all the sides. I know two sides, and I have an angle. I can figure out the other side. That's what we use SOHCAHTOA for, okay? But we also have this relationship, right? Which is alpha or A over sine alpha is equal to B over sine beta is equal to C over sine gamma, right? So we can know that one of them, right, is the hypotenuse, right? So, or this one could be the hypotenuse. So hypotenuse over sine of 90 degrees. What's sine of 90 degrees? Okay. So you bring up a calculator. Even on your computer, you can also use, instead of standard, you can go scientific, right, on your computer, and you can put in some of these values, right? Trigonometric, I want to use sine, right? So there's my sine of 90 degrees. So what happens if I put a sine of 90? So sine of 90, let's do that right. So 90 and then sine 1. So hypotenuse over 1 is equal to, again, we know this, b over b, and this relationship, right, points to the angles that are related to these to the to the points, right? Remember, we labeled the graph, we labeled the points up here, right, way up here. We did that. That this is what they mean. This is A, this is B, this is H, right, or C, right? So C is across from C, A is across from A, B is across from B. That's the relationship. So B over sine of B, kind of thing, right? So we're getting these things all sine on the bottom, sine, sine, sine. Okay. And we can also use this. A squared is equal to B squared plus C squared. And you can take some of these values, B, C, cos alpha, right? And then you can solve for the stuff you're looking for as well. I just think it's easier to use the sine rule because you have partial information and you have 2 of the angles, but you don't have the third one. Or sorry, you have all 3 angles. You have all 3 angles, and we have one side, right? And we want to find the relationships of the other side. Okay, that's how you do it. Okay. So I'll leave this to you, right, to figure out. And then the last question, right, so first you draw the picture, fill in the information you know, then use the formula that you can use, okay? Last example, find the angle of depression, right? So find the angle of depression from the top of a 29.5 meter building to the base of the building across the street, located 12.8 meters away. Again, they're trying to make you not understand what's happening by using these tricky words. So let's draw the building. So here's the building, right? And we can know that the angle of depression from the top of a 29.5 meter building means that I'm actually making a line that goes from here to here. This is 29.5 meters. This is the building, right? So we know we can start drawing the pictures, right? So 29.5 meters, right? That's how tall the building is. And that's how we put this angle, this thing right here. Okay, the angle of depression means this side, this angle here. To the base of a building across the street, 12.8 meters away. So let's make another building. Just to make it different, we'll make it smaller. So this is the second building. We don't care about the height of it, but we know from here to the base of the building is 12.8 meters away. Just to make it proportional, we'll drag it closer. Something like this, okay? So then we draw the line. We draw a line from here to the base of the building. And let's draw this one so that it's aligned with this one, right? So this is the building, and this is the base of the building. This line here is 12.8 meters away. So we will, I wanted to do this, yep. And you can say that this is 12.8 meters. Okay? And now we'll complete the triangle. So we're going to say from the base of the building, right here, to the top of the building. Okay, let's get rid of the buildings. Right? So this is the thing that we're looking for. Right? So looking down, that's the depression this way. This is what we're looking for right here. We know this angle, right? That's a 90-degree angle. Okay, there's your 90-degree angle. We don't know this angle. We can figure this out because we have one angle and we have this. We can use Pythagorean theorem. All right, Pythagorean theorem. We could use Pythagorean theorem here to figure out this angle, but really all we need is this angle. It would be nice right, if we had this angle? We want to find this angle here, right? And we want to be able to solve the triangle, so to speak. So if we wanted to find this side, we could use Pythagorean theorem, right? What else could we do? And Andre gave me, approximately 23.5 degrees. Okay, how did you figure that out, Andre? Right, this is the negative, the angle that's down here, right? I know we're over time, guys. Bear with me. I'm trying to help you guys, kind of figure this out. So what could we use here is what I'm asking for you to figure out this. We could use Pythagorean theorem, and Pythagorean theorem would be, c squared is equal to a squared plus b, the square root of a squared plus b here, b squared, right? So c is equal to the square root of a squared plus b squared. So if we were to do that, and let's do that with our calculator. Again, let's bring that up. And if we said that, we said something like a squared plus b squared. So let's say this is a squared, so 29.5. And by the way, you can use brackets and all that stuff too with your calculator. You can say 29.5, right? And then you want to say squared, right? Maybe it doesn't work. We can use, 29.5. I'm so used to other things. Squared, 870.25. Let's put that inside of our memory plus. There we go. And clear it. And then 12.8 squared, right? And then add that to memory plus. And then now we have memory recall. And then we do square root. And that's the value, 32.1572, blah, blah, blah. Approximately, we want to round it up. Usually what we do is we say 7 becomes, this becomes a 6, right? So 32.16 or 32.2. So we can say that this is 32.2. Is that right? Do you agree? Okay. And once we know those three and we know this, then we can figure these out, right? Because now we have all the relationships, so we can do SOHCAHTOA. Why? Because if I want to find this out, I can use, I have this one, I have this one, opposite over hypotenuse. I can also, if I didn't know this, I can also do opposite over adjacent, right? Without doing this calculation, okay? So there's lots of ways to do it. Using SOHCAHTOA, I don't have to even do Pythagorean theorem, right? Because I have these two things. I have opposite over adjacent. And if you look at SOHCAHTOA, our little formula for SOHCAHTOA down here, let me see if I can find that graph again really quickly. All I need is 2, right? Opposite over adjacent. Well, then I can use 10x. So I can use the arctangent to figure this out. Arctangent of opposite over adjacent. And that'll give me the last one. Arctangent of opposite, 12.8, over adjacent, 29.5, will give me the angle here, arctan, using SOHCAHTOA. Okay? So again, these are the kind of problems that I'm going to ask you to do. And it's going to be problems that you're going to see on like little algebraic and trigonometric problems on your tests. The most you're going to see is something that looks like this. And Samuel had it. Samuel said arctan of opposite over adjacent. It makes sense. Okay. Questions around the stuff we talked about today. It should be coming to you. You should be starting to remember some of this stuff. Without trig and geometry, then doing physics, right, which is the next step next week, is impossible. So what are you doing in lab? Starting next week, most likely Joss will take you through a tour of the framework and get you to do some simple problems with that framework. Okay? Any questions before we go for the day? Because that's it. Okay, guys, that's it for me today. I'm going to stop recording on YouTube, and I hope to see you guys next week at the same time. Take care, and thanks so much for coming up.